Okay, let's look at chapter 4, example 3, reheat Rankine cycle. A Rankine cycle operates between the boiler pressure of 4 megapascal and the condenser pressure of 10 kilopascal. Steam is reheated at 400 kilopascal to 400 degrees Celsius before entering the low pressure turbine. The maximum temperature in the cycle is 600 degrees Celsius. Sketch the cycle on a TS diagram. Okay, so I've put the TS diagram over here. So let's write what we already know. We have the boiler pressure. So if you want to know which one is the boiler will be at 0.2 to 0.3. Okay, so this one is the boiler. Okay, and then the pressure is 4 megapascal. Okay, next the condenser pressure. The condenser pressure is 10 kilopascal. Condenser will be from 0.6 to 0.1. Okay, so this is the condenser. 6 to 0.1, and then it will become 10 kilopascal. Okay, so this line is 10 kilopascal, and then we see that the steam is reheated at 400 kilopascal to 400 degrees Celsius before entering the low pressure turbine. So this is the reheating process. It will be 400 kilopascal and 400 degrees Celsius. Okay, next the maximum temperature in the cycle is 600 degrees Celsius. So 0.5 and 0.3 and 0.5. The maximum temperature is 600 degrees Celsius. Okay, next we need to find the total heat transferred to the boiler, total work output, the overall thermal efficiency, and the specific steam consumption. Okay, so first let's write all the equation that we need. Total heat transfer, number 1. Q in equals to Q primary plus Q reheat. Okay, the primary is the actual value before we add the reheat process, and then we plus because we also have the Q, that is the heat transfer to the boiler that is caused by the reheat process. So we need to plus the reheat process, which is equals to boiler is this one, H3 minus H2 plus, okay, the reheat process is H5 minus H4. Okay, next number 2 is the total work output. Work output is equals to work that is done by turbine 1 plus work that is done by turbine 2. Okay, so it is equals to enthalpy at 3 minus enthalpy at 4 plus enthalpy at 5 minus enthalpy at 6. Okay, next is the thermal efficiency is equals to work net over Q in equals to work out minus work in over Q in. So the Q in value we will get from our solution number 1. Okay, the work in can be found from over here. The number 3 is work in is over here. So it will become H2 minus H1 or V1, V2 minus V1. Then the last one is SSC, which is easy to find, 1 over W net. Okay. So next we need to find all the enthalpy values that we need to find our solution, which is enthalpy at 0.2, 0.3, 0.4, 0.5, and also we also have enthalpy at 0.1, V1, P2, and V1. Okay, next let's find the properties at each state. Okay, so first we find the properties at state 1. At state 1, P1 is equals to 10 kilopascal and also a saturated liquid. How we know this is because this is the TS diagram that we have drawn at P1 over here. Okay, the line is 10 kilopascal and it is at the T set line. Okay, so we can just take the value of P1 equals 10 kilopascal from the A5 table. For 10 kilopascal, P set is 45.81. Okay, P set is equals 45.81 degrees Celsius, and then we have the VF value is 0.001010, and then the enthalpy value is liquid 191.81. Okay, the enthalpy value is equals to 191.81. Okay, so we already have state 1. Then we need to find state 2. At state 2, the pressure is, because it's state 2, we use this line. Okay, this line, the pressure is 4 megapascal. And then, or if you want to convert it, it will become 4000 kilopascal. And then, because the entropy value is the same, S1 is equals to S2, we can find the work in. Okay, the work in. This work in can also be used for the solution for number 3. So work in is equals to H2 minus H1. The entropy at point 2 is something that we don't know yet. So we can just use V1, P2 minus P1, which is equals to, we already found our V, 0.001010 times 4000 kilopascal minus 10 kilopascal. So we will get the value of 4.03 kilojoule over kg. We already have this H1, so our H2 value will become 4.03 plus 191.81, so equals to 195.84 kilojoule over kg. Okay, next at state 3. At state 3, so over here it is a superheated vapor. It is supposed to be superheated. So first, if we want to check at point 3, the pressure is still the same with point 2, sorry. So 4 megapascal or 4000 kilopascal. Okay, the temperature is the maximum temperature, which is 600 degrees Celsius. From table A5, okay, let's look at table A5. From table A5, P3 is 4000. 4000, the T set is 250.35, if I'm not mistaken. 250. T set at 4 megapascal is 250.35 degrees Celsius. So we find that T3 is bigger than T set. So we know that it is a superheated. Okay. So if it is a superheated vapor, we need to look at table A6 to find our properties. Okay, let's look at table A6. From table A6, we find that H3 is equals to 3674.9. Then S3 is equals to 7.3706 kilojoule over kg. Okay, next state 4. At state 4, it is also superheated condition, but we know that the entropy value S3 is equals to S4. Okay,